going to be used for functions that are defined implicitly. I don't think we normally in math talk about implicitly defined functions. On this page, I kind of have an example in that first column. That would be an example of an implicitly defined function versus we're going to compare it to what we would call an explicitly defined function. In math, for the most part, you're dealing with an explicit function. An explicit function is always in the form of like y equals, and then like everything on the other side is in terms of x. An implicit function is going to be one that mixes together x and y's on the same side of the equal sign. Some like common functions that you might be familiar with, just thinking about last year in pre-calc, most conic sections are written implicitly because you have x and y on the same side of the equal sign. So when it comes to implicitly defined functions, like this first one, y minus tangent x is equal to 0, that is considered an implicit function. We can rewrite that one a lot easier by moving that tangent over to the other side, and I would have y equals the tangent of x. That is a lot more friendly to take the derivative of. We know that the derivative of tangent is secant squared. Same thing for this next row, y cubed plus 2x equals 5. This would be called an implicit function because we have x and y's mixed together on the same side of the equal sign. If I wanted to make this an explicit function, we're going to have to, let's see, subtract the 2x from both sides and then take the cubed root of both sides. That one we can easily convert it into an explicit function. Even this one that looks kind of simple, x times y equals 8, that would be called an implicit function. X and y's are mixed together on the same side of the equal sign. An explicit function, dividing both sides by x, would be y is equal to 8 over x. The issue we run into for some of these is like this last example. This is a pretty crazy looking implicit function. I have y cubed is plus 2 secant of y is equal to x minus 8. That is one where you can't, like it's impossible to solve by hand that one in terms of y. Like you will never be able to get y by itself. So we don't have a way to find it explicitly. But in calculus, we still want to find a way to like find its derivatives. We can talk about its slope, find tangent lines, and things like that. So what we're going to be focusing on today is how we find the derivative of these functions that have x and y mixed together, or where it's just not this easily just y equals everything else. So when it comes to explicitly defined functions, we know how to take the derivative of those. Sometimes we don't. So to start off with just some like easy, simple examples, I just have these derivatives, and I wrote my derivative notation a little bit differently. For implicit differentiation, we are going to use the Leibniz notation for the derivative a lot more often because we want to see what we're taking the derivative with respect to. So we haven't used it as often. We haven't really explained what it meant, but it does become important for this topic. So like that first problem we see, I see the d dx of x squared. We know, or maybe we don't know, but we're about to know, this kind of symbol means take the derivative, and that denominator tells you what you're taking the derivative with respect to. So when I see d dx, that means take the derivative with respect to x. And when I say with respect to x, like most of the time we don't need to say that clearly because we're almost always taking the derivative with respect to x. Like if I say find the derivative of sine of x, it's understood to be with respect to x. And we know the derivative of that. The derivative of x squared is just going to give us what? 2x. Like we know that. Where that can change is we can technically in math take the derivative with respect to whatever variable we want it to. So like on this one I have d dy. That dy means take the derivative with respect to y of y squared. Well, what do you think the derivative of y with respect, what's the derivative of y squared with respect to y is going to be? 2y. Same rule, because we're taking the derivative with respect to the variable that we have. Where we are going to have to use implicit differentiation is when we have a mismatch and what we're taking the derivative with respect to, and then the variable that we have. So when you're looking at that third one, you're saying, hey, take the derivative, I'm going to abbreviate with respect to, with WRT, with respect to x, but the variable we have is in terms of y. Those don't match up. So this would be an example where we have to use implicit differentiation. And the way the process we're going to go through, this is a very simple example, but just to kind of see how it works. When you're doing an implicit differentiation, you first take the derivative like you normally would, like without the with respect to. So when we see y squared, what's y squared? And then how we fix and not match the x, we're going to multiply it by kind of like a fixer piece. And that fixer piece is going to be d, the variable you had, over d, the variable you wanted. So in other ways, we're multiplying it by the derivative of y. But we're going to write it in that notation of dy dx. To give you some other kind of simple examples before we get to kind of like the AP level version, on this next version, I have 3 problems. That first one we just did. Implicit differentiation it's really coming from the chain rule. I could go into the theory of why it's a chain rule, but I think just seeing the process is a little bit easier to understand. So again, this is that first one that we just did. And again, the process is, this is the derivative with respect to x, and that x does not match the y. That's your big clue. You're going to have to use implicit differentiation. So again, the derivative of this one would be 2y. And then we say, well, we had a y, I wish that was an x, and we're always multiplying. Technically, we've always been doing implicit differentiation, we just didn't know we were doing it. For example, the second one I have d dy of y squared. Would you technically need to use implicit differentiation for this one? No, you're taking it with respect to y, and you have a y. But if you did implicit differentiation, you're not going to end up with the wrong answer. And what I mean by that is, the derivative of y squared is 2y. Well, you had a y and you wanted a y. What did we say dy over dy is going to be? Just 1. So that's why we just can do it normally without the implicit differentiation. We can take the derivative with respect to any variable. This last one, I have d dt y squared. We just looked at PVA problems. Sometimes we want to take the derivative with respect to t, with respect to time. So if I'm looking at this one, I'm taking the derivative with respect to t, but I have a y, so we're going to take the derivative like normal. The derivative of y squared is 2y, but then we had a y, I wish it was a t. So that derivative is actually going to be 2y times dy dt. Always multiply when you're doing that fixer piece. And again, you have to do that when you're taking it with respect to a variable. With the variable you're taking with respect to doesn't match the variable that you have. Questions so far before we look at some more of like the AP type questions? All right, let's look at this first one. Start off simple. I think implicit differentiation can kind of make people feel like weird. So like if I look at this one is one we technically don't need implicit differentiation for, but I think it's nice to look at just to kind of talk about like the theory and the process. Like if I just told you normally y is equal to 3x squared, what would you say the derivative of 3x squared is? 6x. Like that's not changing. And we would use y prime. That's the notation we have been using. Kind of a long way to do this problem, which is not how I would expect anyone to actually do this problem, is technically we're taking the derivative of both sides with respect to x. So like the long way of thinking about this problem is you're taking the derivative of y with respect to x, and you're taking the derivative of 3x squared with respect to x. Technically, y is a variable. What would be the derivative of y? What's the slope? What's 1? That's what I'm trying to say. So what's the derivative of y would just be 1. So you're like, that would be 1. I had a y. I wish it was an x. And on the other side, what's the derivative of 3x squared? 6x, we had an x, that's what we wanted, so it didn't really matter. We've learned already what's the same thing as saying dy dx. dy dx is just another way, a fancier way of saying y prime. So you technically have been doing implicit differentiation, like I don't want to say like it's something new. We just haven't had to worry about it because we've just only been taking the derivative of explicitly defined functions. Where this changes is when our function is no longer explicitly defined. So something like this. I have the sine of y is equal to 3x squared. There's a graph of it. We often don't need to know the graph of it, but these implicitly defined functions often form things like curves, like ovals, circles, like waves. They have all sorts of weird shapes that they can have. But if I want to take the derivative of this is what we're going to focus on today. This is not explicitly defined. It's not in the form of y equals, but we can take the derivative implicitly. So when we take the derivative implicitly, if the variable doesn't match, we have to multiply by that fixer piece. So looking at this equation, which side, left or right, are we going to have to worry about the implicit differentiation? If I'm taking it with respect to x. The left. So the left side has the y in it. So I'm going to do the easy part first. 3x squared I don't need to worry about because it has the x in it. The derivative of 3x squared is 6x, easy enough. The derivative of sine of y, so think about it. What's the derivative of sine? Cosine is the cosine of y, but then we have the fixer piece. I had a y, I wish it was an x. That is the derivative. It's not often how we will leave the derivative, but that is going to be an expression for the derivative. Often these problems, what I find students have the most trouble with once you start seeing how it works is not the calculus, like you can take the derivative easily. It becomes the algebra part because often we'll need to solve this expression for dy dx. This one's pretty easy to solve for. If I wanted to get dy dx by itself, which is the same thing as y prime, dividing both sides by the cosine of y, the derivative would become 6x over the cosine of y. What's interesting about these problems, like derivatives with both x's and y's mixed together. So it ends up complicating some things. Like if we say find a tangent line, you have to plug in both the x and the y coordinate to find a slope. These types of problems are also why we need to have the second derivative test. Like we're not going to be able to make a sign chart with something that looks like this, where we have x's and y's mixed together. We're going to have to rely on other ways to find extrema and things like that. Next example, I just kind of took the same one and adjusted it a little bit. Same graph, but I am going to take the derivative with respect to t. So go ahead and try that one for me. This one you will have to think about it doing implicitly on both sides, because one side has y, one side has x, but I'm taking the derivative with respect to this variable t, which often is going to represent time or something like that. And again, don't overthink it. Just find the derivative as you normally would, and then multiply it by that like fixer piece when the variables don't match. So if I'm trying this one, again, we already talked about the derivative of sine. The derivative of sine is cosine. I had a y, I wish this was a t. And then on the other side, the derivative of 3x squared is 6x. I had an x, I wish it was a t. And that one I'm not going to solve for anything because we have kind of two different derivatives going on, which has a whole nother meaning, but that's for after Thanksgiving. To check what you are understanding, go ahead and try those two for me. So one thing about implicit differentiation is any rule that we have learned or any rule that we will learn can still show up. So you can still have things like the quotient rule. You can still have things like the chain rule. You have the product rule. All those rules apply. The only thing we now have to be aware of is what variable we're taking the derivative with respect to. And if the variable doesn't match, we have to multiply it by that fixer piece. So go ahead and try those two for me. And there is a third one, but it's a little bit trickier, so hold off on that third one for a second. Yeah.
So, technically,
Yeah, the issue is like y prime is the same thing as ydx, and those aren't matter. Those are just y kids. We don't really
but if you were
we're not going to separate those. Like that dx and dt is like one symbol. Because it's representing the derivative of x with respect to time. So we're not going to split it up like that. I get what you're saying.
okay,
But we're going to think of it like if it looks like a fraction, we're going to treat it like a single. And hopefully on that second one, you are using the product rule because the sine of x times the sine of y. And don't worry about solving for dy dx. I just want to worry about us taking the derivative right now. So let's look at that first one. We are differentiating both sides with respect to x. So I know that whenever I take the derivative and your variable is not x, we have to think about this thing called implicit differentiation. So going across the derivative of sine of x, I can do this one as normal. The derivative of sine of x is cosine of x. Plus sine of y, I do need to be careful with this. The derivative of sine is still cosine, but this had a y in it. I wish it was an x. And then equal to, I have y squared. Also need to be careful with this one. The derivative of y squared is 2y. I wish I had a y when I was taking the derivative with respect, or I had a y, I wish it was an x. That is all that problem was asking us to do. It asks us to just take the derivative of both sides. Looking at this second one, we have a product. This is sine of x times sine of y. You do want to be careful when you're doing the product. That like fixer piece is only going to show up when you take the derivative of y. So like if I'm working on this one, I'm going to have the first times the derivative of the second. The derivative of sine is cosine. This had a y in it. I wish it was an x. Plus the second times the derivative of the first, and that's equal to another implicit differentiation, 2y dy dx. And one thing that I want us to kind of be careful with, like I know dy dx is the same thing as y prime. I'm going to advise us to not write it as y prime because of kind of where this is headed. And we're also going to think about that dy dx as like a single symbol. So like when we see dy dx, yes, that is the derivative, but don't treat that like a fraction where you can separate those. We will eventually, but not this semester. Questions on those two before we do on to chain rule? All right, see what you can do with this one then for me. So this one is the sine of x times y. I think this was a little bit complicated because we have to do the chain rule and the product rule and implicit differentiation. So see if you can do that one correctly. Don't worry about simplifying anything. Just see if you can find the derivative. Still taking the derivative with respect to x.
is there such thing as a dxy over 2 or no?
Not in 2 dimensions. So not till top 3. And those are called scalars. That's a different thing. And again, if you need help kind of thinking about this one, remember chain rule, you take the derivative of the outside first, leave the inside the same, then multiply by the derivative of the inside, and that's where kind of the product rule and everything is showing up. So the inside of this is x times y. So if I'm taking the derivative of this one, the derivative of sine is cosine. Leave the inside the same. So I haven't taken the derivative of y yet. I don't need to add the dy dx. Times the derivative of the inside. This is the product, so I have the first times the derivative of y plus the second times the derivative of the first, and then equal to 2y dy dx. This piece right here is coming from the chain rule. And I had to do the implicit part when I took the derivative of y. So you can see how these problems can kind of get, like, they get ugly because there's usually like a lot of parts going on with them. And again, I do normally see the parts that students struggle with most on these is not normally the calculus, but like the algebra when it comes to like simplifying them and manipulating them. Any questions on those three before we look at just a few more examples for today? Yes, Becky.
How did you find the derivative of x times y?
The product rule, because this is x times y. So I had the first times the derivative of y, which is 1 times dy dx, plus the second times the derivative of x.
Okay.
Product rule. All right, so here's one that I want to do. We know that this is really just a process for taking the derivative. So like anything that we have ever done with the derivative, we can also do when we find a function implicitly. So I wanted to start off with like tangent lines, and then we're not going to do all the notes today, but we can do things like finding extrema, we can find second derivatives, we can find concavity. I could rewrite this into be like a PVA problem, like anything we have ever done with the derivative, we can also do implicitly. So it just has to be something that you have to always be aware of. So here's some ways that the AP exam and myself will word questions. So looking at these two questions, they actually read very, very similar, but they mean slightly different things. So I have this graph. I'm not going to call it a function because it actually fails the vertical line test, but I have this curve, and this first set of instructions just tells you to differentiate both sides with respect to x. When you see that set of instructions, that just means you need to take the derivative, making sure you do it implicitly if needed, but you can just stop as soon as you take the derivative. More often, though, on my tests, AP exams, and moving forward, it will say find dy dx in terms of x and y. When you see the instructions worded this way, it's going to add one more step. You're still going to need to take the derivative of both sides, but then you need to do the algebra to basically solve for the dy dx and isolate the dy dx. So let's go ahead and take the derivative of both sides. Again, we're doing it with respect to x. So anytime we take the derivative of something that is not x, I need to make sure I do it implicitly. So y cubed is going to become 3y squared. I had a y. I wish it was an x. 2 is a constant. What's its derivative? 0. That's nice. And then we had the derivative of x, which is going to be 1. And then the derivative of sine, which is cosine. And then again, I had a y, and I wish it was an x. That first part of the instructions is just telling you to do that piece. The second part, though, is asking us to find dy dx in terms of x and y. So when we see it in terms of x and y, that basically means our final answer should be dy dx equals, and then things with x and y on the other side. Solving for these, there does tend to be like a general pattern you want to do. You want anything with a dy dx on one side the equal sign, everything else without a dy dx on the other side the equal sign, factor out the dy dx, and divide by the leftovers. So it tends to be pretty quick steps. So if I'm looking at this one, doesn't matter which side you get the dy dx is on, I'm going to get it on the left-hand side. So I'm going to add this cosine y dy dx to the other side. And again, this is multiplied, so we're going to think of those as like a single term. So we have 3y squared dy dx. I'm adding this term to the other side, so it becomes plus cosine of y dy dx. And I want anything without a dy dx on the other side of the equal sign. So there's nothing to move over from the left, but I do have that one left over on the other side. And then if I want to solve for dy dx, I notice that both of those terms have a dy dx in them. Well, if we have terms with something in common, we can factor it out. So I'm going to go ahead and factor out that dy dx. These steps kind of show up over and over again, so kind of good to follow that process. And then if I want dy dx to be by itself, I just want to divide by what was left over in parentheses. So like my final answer, the derivative of this function is the same thing as saying 1 over 3y squared plus the cosine of y. Questions on how I found that derivative and then isolated dy dx. All right, you're quiet, so let's just keep tracking along. Go ahead and try the last part of that question. So it tells you to find the equation of the line tangent to the graph at 2, 0. Probably been a while since we wrote a tangent line, but just to remind ourselves, what two things do we need to write a tangent line? We have to have a slope, and we also have to have the point. So they gave us the point. There's your x1 and y1. How do we get the slope? Where does the slope come from? The derivative. And what is the derivative? Dy dx. What's different when we've done something implicitly, we're used to just plugging in the x value to find the slope, but now we have to pay attention to the variables. For this particular example, which coordinate are we actually going to have to plug in to find the slope? The y's. Sometimes you plug in the x's and the y's. Sometimes we'll just plug in the x's. In this case, you're just plugging in the y's. So finding that slope, I am finding the derivative, dy dx, at the coordinate 2, 0. So I am going to plug in that y coordinate of 0. 3 times 0 is 0. The cosine of 0 is 1. This one works out pretty nicely, and your slope is 1. So then writing the tangent line, I have y minus the y coordinate is equal to the slope times x minus the x coordinate. You can leave it like that, or simplifying that becomes y is equal to x minus 2. So again, I do like implicit differentiation because it does force you to review a lot of stuff that we've done, like tangent lines, intervals of increasing and decreasing, extrema, and all of that. Questions on that problem? All right, let's do, what time is it? Try this one for me. There you go. Try that one for me. So I give you a function, or not really a function. That is a slanted ellipse, is what it graphs. And I want you to find the equation of that tangent line. So we have x squared is equal to x times y plus y squared, which is equal to 7. You want to take the derivative of that implicitly. And you're going to take the derivative with respect to x. You can assume you're taking it with respect to x if it doesn't state that. Solve for dy dx. And then you can plug in the coordinate to find the slope, and then use that to do the tangent line. We'll say be careful when you're finding the derivative because this is an x times y, so you will have to use the product rule somewhere in there. But try that one. This one does end up being quite a bit of algebra, but you try it before I just jump in and go over it. When you're stuck, just let me know. Always differentiate both sides. But that 7's a constant, so it's just going to go to 0. Okay.
So,
Say it, Sarah.
so this would just go to x times dy.
Mm-hmm. And then basically when you solve for dy dx, you'll get like anything with a dy dx on one side, and then everything else on the other side of the equal sign. It doesn't say where it's going to be implied to be with respect to x. And if you're still taking the derivative, you can kind of think of two ways to do that product. Some people like thinking of it as negative x times y and have that negative kind of attached to the x. The other way to think about it is find the derivative of x times y and then distribute the negative across. You'll get to the same answer. There's kind of like two different ways to think about it. This is definitely a very algebra heavy topic. If you want to check your derivative, I'm not going to finish it quite yet right now. So the derivative of x squared is going to become 2x. I'm going to think of this as a negative x times a y, so you might have done it a little bit differently. But I'm going to have the first times the derivative of the second. The derivative of y would be 1 dy dx. And then plus the second times the derivative of the first. The derivative of negative x would be negative 1, plus the derivative of y squared would be 2y dy dx, and then the derivative of 7 is 0. One of the most common mistakes I see, I feel like every year I teach it happens on the test. Whenever there's a number by itself and you're taking the derivative of both sides, some people just mess up and just bring that number down. But just remember that the derivative of a constant is always 0. So then if I clean this up a bit, we have 2x minus x times dy dx minus y plus 2y dy dx, which is equal to 0. So to let you finish that out, or let me check your work if you got stuck, you should have 4 terms in that derivative. And basically to get dy dx by itself, you want to get anything with a dy dx on one side of the equal sign, anything without a dy dx on the other side of the equal sign. Doesn't matter which one you do. And then factor out the dy dx and divide by the leftovers. And I will show you when we go over it, depending on which side you get the dy dx on, you might have like a complete opposite answer than me, but it will still work out the same way. And then once you have dy dx, then you can plug in the coordinate for the slope and then write the tangent line. All right, so there is some more of my work. I will go ahead and say, get this out of your head that these problems are often not going to be short problems. They usually take up some space. So I found my derivative, and then we're at the point where I just kind of cleaned it up a bit. And then that second line of blue, I have everything with a dy dx in it on one side of the equal sign, anything without a dy dx on the other. It doesn't matter which side you get the dy dx on, as long as you separate them. And then the idea is both those terms now on my left-hand side have a dy dx in them, so I can factor it on the outside. And then how do I get dy dx by itself? Divide by the leftovers. One thing you want to be careful with checking your answers if you had gotten your dy dx's on the right-hand side instead of the left, you would have gotten the same answer as me, but the signs of all of your expressions would have just been the opposite. Point out, because oftentimes, like if this was a multiple choice question on the AP exam, you'll like work it out and you think you don't have an answer, but if like you see an answer where every single term had a different sign, then that's going to be an equivalent answer to what you found. So that's the slope, or excuse me, that's the derivative. We're still not done because it did ask us to find the tangent line. We were doing the tangent line, I already forgot, at 2 comma negative 1. So from here, now it's the easy part. If I want to find the tangent line at 2 comma negative 1, to write a tangent line, you have to have the point and the slope. It is going to come from the derivative. So whatever your derivative was, I'm going to plug it in. This derivative, we have to plug in both the x and the y coordinate. So I have like 2 times 2 plus the negative 1 over the negative 2 plus 2 times negative 1. Cleaning this up a bit, that's going to be negative 4 minus 1, negative 5 over negative 3, no, negative 4, which is the same thing as 5/4. So then final answer, I have y minus the y coordinate is equal to the slope times x minus the x coordinate. And that would be the tangent line for that problem. So I do want to go ahead and warn you, like we still have some more notes to do with this, like we have to talk about like how to find the second derivative, which kind of has its own process, and some other things we do with these types of problems. These are like the first problems you're going to have that are not, like there's no shortcuts, there's no like short ways to do them. Like they often take up like maybe half a page, a third of a page, might be longer than that. The algebra is important, so make sure you're the type of person that shows kind of messy work. You at least are a little bit organized so that your work follows clearly. I'm going to stop here for today just to give you some time to start the homework. Hopefully you'll do some of the homework tonight. Realize you can't do all of it because I have not taught you everything. But the first few questions are just find the derivative, which is something that you are able to do. So that concludes what I want to get done with class. Again, still have 4 more slides of notes, and they're actually not like the shortest ones, so we might take notes tomorrow, then they might even continue till Friday, just to give you an idea how long they are. What I want you working on is this homework number 8. So again, I took out homework 7, so there is no homework 7. Don't worry about it. It is in the textbook. I want you to do 4 through 40s, multiples of 4. Please skip 20. You don't need to know how to do number 20. And then 46 through 56 evens, but skip 56 because you don't need to know how to do that one. You will have Wednesday, Thursday, Friday to work on all that. I would recommend this is not one of the homeworks you want to get behind on. It tends to be one of the longer ones for students just because it is very algebra heavy. And so I don't want you to think that you can do all this in one night. This is definitely not a homework assignment that you can do in one night. And then next week, we're basically going to be reviewing, working on our briefcase binder, and then our test day of next week. So y'all can go ahead and get started on the homework. Take about 15 minutes to make some progress on that, or to ask me questions on the notes if you want anything clarified, and then we'll pick right back up with that tomorrow. And if you're at home, feel free to ask me questions or leave, I guess.